In this Mathematica tutorial, I'm going to show you how to calculate this integral using a trig substitution. If you're interested in that, keep watching. Okay. Now, I'm a little camouflaged, but I'm wearing this shirt from... It was a gift. It comes out of a recent book. I'll show you this one. So it's just about a month since we published this. Sometime in the future, I'm going to show you how to do some of the professional diagrams that we did in Mathematica in this book. So find one. This, for example, we did this in Mathematica. I'm going to show you eventually how to do that and some others involving text. Anyway, but we'll get on to this problem to compute this integral using a trig substitution. Okay, so first of all, you want to look at this and think, well, what options do I have? All right, so you've got integration by partial fractions, which we did in the last video. And actually, I think you could do this one with partial fractions if you just factorize this denominator over complex numbers. Okay, but look, if we have enough time, maybe we'll do that too. All right, but this one will be about trig substitutions. Now, what you want to keep in mind is some of the trig relationships, like sine squared plus cos squared is equal to 1. Okay, so that is what we're going to take advantage of in order to calculate this integral by a trig substitution. So where do we begin? Now, this one will work with a tan of y substitution. So if we let x be equal to tan y or tan theta, up to you. I'll go with tan y because I could easily type that in on the keyboard. So we'll say now I'm not going to execute this in Mathematica, I'm just going to let this be one big comment, and then later we'll calculate this in Mathematica. Okay, let x be equal to, so I almost want tan of y, but not quite, right? You've got to think a little bit in advance, like when you're playing chess. How is this going to play out? All right, so now notice I've got a 4 in there, right? 4 is a square, so that's helpful. All right, so we want to let x be equal to 2 tan y. Now why that? Because when I square it, I'll have a 4. I'll have a 4 right here, and I'll have a 4 here that can be factorized out, okay? So that's why. And also, due to the derivative of this with respect to y, we'll be able to find some nice cancellation that will happen. Okay, so really these trig substitutions, you get better at them with some practice, because that practice inspires the way you want to set this out. Okay, so you might have some failures, that's okay. Just learn by the failures. All right, so now step 1 is to differentiate this. Now, you could do this by hand, right? So you want to observe that tan of y is sine of y over cos of y, right? This is just a trig ratio that you learn when you first learn about trigonometry. So let's open up a palette and pull out a fraction. Basic Math Assistant. All right, so I'm looking for fraction. Okay, now I'll close that, and then I'll just say right, sine of y over cos of y. All right, now this is tan of y. Tan of y is sine of y over cos of y. All right, but we're interested in twice tan of y, so let's just put a 2 in front of that. Okay, now you could differentiate this by hand, and you would want to use the quotient rule for differentiation. Okay, but since this is not a video about differentiation, let's just use Mathematica to do that part of it. Okay, so I'll turn all of this into a comment so that I can do a derivative in Mathematica. And I'll just put a big D, and then I want to differentiate tan of y with respect to y. Okay, shift enter, see what we get. Sec squared. Now if you remember what sec is, it is 1 divided by cos of y. Okay, sec of y, 1 divided by cos of y. Okay, so twice that. Well, this will be just twice this, right? Okay, so now that we have that, let's come down here and continue. And so I can take the comment off to make it brighter so we can see it. Okay, so then we want to say, now I'll pull up a fraction to make this look like what we would write if we were writing out some calculus. Actually, I want to differentiate x with respect to y, right? Okay, so this is the derivative of, so I have d on dy, and we differentiated 2 tan of y with respect to y. Okay, so that 2 comes through, and we've already deduced that this is twice sec squared. Okay, so I'll copy and paste and enter. So this is 1 on cos. Now often when you write this by hand you will write cos squared y, but I'll just put the squared part right there, and what I mean is to square the whole cos. Okay, so now I've differentiated x with respect to y. Oh, whoops, we need the 2, okay. And now I'll get rid of this. And now what I'm doing is I want to use this in aid to knowing what substitution to make. Okay, so this tells me that if I were to rearrange this as if this derivative is a fraction, but it is not a fraction, what I would do if I'm thinking of this temporarily as a fraction, what I do is I multiply both sides by dy, and that says dx equals twice dy over cos squared y, right? But that's an aid to memory of the rule that I can substitute dx with 2 dy over cos squared y. Okay, now we can go back to our integral and use that substitution. Oh, whoops, I've accidentally executed this, so I'll come back, turn it into a comment and do it again so I get that side cell notification out of the way. Okay, I'll take it off now. It's nice and colorful. Okay, so we've let x be 2 tan y, and now we can say that this is equal to, having replaced dx with 2 dy on cos squared. Okay, now we've made the replacement. We also should replace x with 2 tan y. So let's do that also. All right, I'll put a bracket around this because it's all getting squared. Okay, and now we see again why we put the 2 in there, because when we square this, we'll have a 4 right here, and that can be outside of the bracket, and we can get rid of this bracket here. Okay, now you see you can factorize this, so why don't we do that, and we'll write this as 1/4 in the numerator. Okay, so 1, 4, and there we have it. And let's put a bracket around this because we want to then multiply throughout by this cos y squared right there. Okay, and we'll pull this 2 over here at the same time. Okay, now that's probably enough to go on and include a new line. So let's include a new line. Now 2 over 4 is 1/2. Okay, but we want to multiply this cos squared y through and expand over this bracket. All right, now tan squared y is sine squared y over cos squared y, so we can cancel the cos squared y in that. And when we do that, we have sine squared y, and then we will move this. Okay, so now having expanded that cos squared y over this sum, distributed over the sum, we have sine squared y plus cos squared y. Okay, if you remember your trig rules, that is equal to 1. Okay, so let's come down and say that this is just 1, right? And, well, we don't need that in the denominator, right? So we can get rid of it. All right, now this is very simple. This says we have the integral of 1/2 with respect to y. Okay, that's easy. It's just 1/2 y. So let's come down to a new line and write 1/2 y. All right, but I want, I think I'll go for a fraction here. So 1/2 y, and then don't forget at this point to put plus c, right, in your calculation. Okay, now remember what y was. Y was equal to 1/2 f. X, if you look at this, you divide throughout by 2. Tan of y is 1/2 x. Okay, so the inverse function to tan is arctan, inverse tan. All right, so that says that y is equal to the arctan of x on 2. Okay, so new line. Y is arctan x over 2. All right, and that is the integral complete. Okay, so we will turn all of this into a comment so that we can actually check our calculation in Mathematica. All right, so let's copy this because this is working code in Mathematica, or you could just write out integrate 1 on x squared plus 4 comma x, and that would do the same thing. Okay, shift enter, see what we have. Well, we get 1/2 arctan of x on 2. Now that's exactly what we have here, right? But this is one antiderivative, and this is the general case, right? Because any constant there will do. It will be an antiderivative of the function 1/x squared plus 4. Okay, so that's all of that. Now, next I want to show you what would you do if you wanted to make all of this look pretty and write this and turn it into a pretty PDF file. Okay, so for that, I'm going to show you how you would do this in LaTeX. Okay, LaTeX is free software. So I'll open that up. Now, where have I got that? I've got a folder on my desktop. Okay, I'll just show you, put it over here. Here's my folder. Now this folder is, it's a cover letter that I've written to apply for jobs. So I've opened it up. Now the job was about typing up some things for doctors, okay, that I've applied for. Cover, now this is a tech file. We'll open it up. So I'm using WinShell together with MikTeX, right, which is a LaTeX system. So I've opened up a template, all right? So it's good to start out with a template. Now, when you have MikTeX and WinShell, you get these buttons up here for lots of Greek letters and other symbols. If you're starting out, that's really handy. Okay, so I'll show you. Now it just says CV and my name, and then some stuff that we don't need. Okay, so I can get rid of this, and then I can show you how you would write this up in LaTeX. All right, so now I wonder if I can just copy some of this. All right, let's try it. I'll select this, I'll right click, copy as LaTeX. Okay, copy as LaTeX. Then I'll come down here and I'll paste, Control V. All right, so it has given me the LaTeX code for that integral command. Okay, but I need to say that that's an equation, so let's go begin. Okay, I'll go EQN array. EQN array. asterisk, and then end eqn array asterisk. Okay, and then when I do that, I need the and symbol equals the and symbol, and then what I'm looking for is the next thing that I included. So what did we do? We then simplified that. Let's come down. We simplified that like this, right? Okay, so let's copy as LaTeX. Okay, copy as LaTeX, paste. Okay, Control V, and there's the code for that. And then I'll put comma. Now this is 2 backslashes to make a new line. And then I'll come down here and go and equals and then what did I simplify that as? Simplified that as this integral right here. So I'll go copy as LaTeX, come down here, paste, and then let's suppose we stop there. Okay, now what I do next is I press this PDF LaTeX button up here, PDF LaTeX. All right, often you need to do this a couple of times. I don't know why this is going slow. Okay, press it again. All right, so then I'll minimize this, and now I go open up the folder again, and I find the PDF file that's in there. Okay, so I'll open this up and I'll show you. All right, look at this, beautiful. We have that integral that we were calculating. Okay, so you could incorporate this and submit this sort of thing in your assignment. Now, if you're writing an assignment, it's nice to learn this because maybe one day you'll need to write something pretty. Okay, but if you're learning, it's often a good idea to write things by hand. Okay, because you can learn, make associations between writing and learning. I don't know how this works. I'm not a psychologist, but I recommend writing things out by hand when you're learning. Yes, so okay, so that's how to do that in LaTeX. Now, I made one other suggestion that we might be able to do this by partial fractions. Okay, so let's give it a go. Come down here into a new cell, and let's see whether or not we can write this, complete this integral using partial fractions. Okay, so what I want to do is look at the factorization of x squared plus 4. Okay, now I happen to know that that can be viewed as the difference of two squares, provided you say that 4 is equal to minus 4i squared, where I is the square root of minus 1. All right, let's just check that. So what I'm saying, now when you enter the square root of minus 1 in Mathematica, uppercase I is used for that. All right, so let's square 2i. Okay, shift enter, we get minus 4. All right, so if we put a minus in there, well, what we've deduced is that this is equal to 4. All right, so I put an equals in there. Now this is a question: are these two quantities equal? All right, shift enter, true. Okay, all good. So that says that we can express this integral right here as the difference of two squares. You see, and why do we want to do that? So that we can factorize this denominator. Okay, so now let's do that. Now, well, what we need to notice is that, remember, a squared minus b squared is equal to a plus b times a minus b. Okay, and that's what we want to use here. I'll make this a comment. Okay, that's what we want to use here, and so this is x plus 2i times x minus 2i. Okay, so now that is good enough to start to use partial fractions on. But let's just double check this. Okay, I'll copy this, come down here, paste, and I'll write expand. Right, just to double check. Okay, that says x squared plus 4, so we're good. All right, so let's continue. Okay, I'll copy this. Now remember the technique of partial fractions. We want to say this is a over the first multiplicand plus b over the second multiplicand. That thing which is to be multiplied. Right, so I'll copy this, plus paste. Okay, get rid of this one, get rid of this one. Then we put in a and b. All right, now that we have that, we think of a and b as two functions of x. Now they could be complex functions, that's okay. Right, now you would recombine these. Okay, so you add these fractions. All right, so to do that, you want common denominator, but we already know what that is. Right, so we're multiplying numerator by that, denominator by that, and on the other side, numerator by this, denominator by this. Okay, copy, come down to a new line. Now we know that this is just x squared plus 4. Okay, so let's put that in. X squared plus 4, x squared plus 4. These denominators are common, so that's great. All right, so that means that we can put them over this same denominator as in the numerators. Plus, okay, I can do this. That's what I'm trying to say. All right, now you want to expand this and look at the coefficients of x and the constant terms. Okay, so I'm going to just come down here and get Mathematica to do that. So write expand, shift enter. All right, and now look, you want to collect like terms. Okay, so what we can do is write collect, and then I want to collect the coefficients of x. Okay, shift enter. All right, it's done that hard work for me. So press enter and copy it out. And actually we should come down to a new line, right? So you can see all of the working. Copy this out, paste that right there. Okay, I want to have the x's in front. All right, and then I'm going to write this in such a way that yeah, let's just put a bracket around it. Okay, good. All right, so now that we've deduced that, remember we were comparing the two of these, okay? All right, so x squared plus 4 is 4 plus x squared, so that's okay. Now we want to compare the numerators, all right? Because we have, so this 1 is equal to 0 times x plus 1. All right, so we must have a plus b equals 0. Okay, so this says a plus b is 0. Oh, whoops, plus. Okay, also, this expression over here has to be equal to 1. Okay, so look, we can factorize the 2i out of this. Let's do that. 2i, okay. Yeah, all right, now what we want to do is divide both sides of this second equation by 2i. All right, so let's do that. 1 over 2i, whoops, over 2i. Okay, and then we can get rid of the brackets. Now, 1 over 2i can be written as something where the complex number has I in the numerator. Okay, so in other words, I can multiply numerator and denominator by I. Okay, so let's do that. All right, I squared is minus 1. Okay, multiplying numerator and denominator by I squared is minus 1, so this becomes minus 2. Okay, so in other words, minus a half I. Now, this will be a little bit nicer if we just say multiply throughout by minus 1. Okay, so that will say a minus b is equal to 1/2 of I. Is that correct? Just have a think about that. Yes, all good. Okay, now we want to consider this as a simultaneous system of equations. Okay, you could solve this by hand, and that's probably the way to go there. So you would add the two of these equations, okay, or you could get Mathematica to do it. So I'll show you both ways. Now, if we add the two equations, what we get is twice a, and the b vanishes, right, on the left-hand side, is equal to 0 plus 1/2 I. Okay, so straight away, dividing throughout by 2, you find that a has to be equal to 1/4 of I. Okay, so that means that b has to be equal to minus this. Okay, and that solves the system. So that's doing it by hand. Now let's come down to a new cell and we'll show you how to solve a system. Right, solve. Right, what was the system? These two equations. So I think from memory I just put in a bracket. Yeah, I think so. Right, now I need a comma between these. And then you might want to say that you're solving for a or b, but I don't think you need it here. So let's try it. Okay, so we get a... Oh, I see the problem. Okay, I need an equals equals there. Shift enter. All right, good. So that solves it, and it agrees with what we found calculating it by hand. So very good. Okay, now that we have this, let's use this in our partial fraction calculation. All right, so come down here, and we were working on this. Okay, also paste that again. Now a plus b. Actually, what I want is this line right here. Okay, I'll copy that, paste. Too many equal signs. All right, we found that a is 1/4 of I, and b is minus 1/4 of I. Okay, so now that we have this, that makes this much easier. Okay, so let's just show. Now, 1/4 I is a constant, but first of all, I want to break this up into two integrals. So we can do that. Right, so it's the sum of these two integrals, because you can break up integrals of sums as sums of integrals. All right, and next, pull these out, because that's another rule that you can do. Pull out constant terms. Put a 1 there, and the same for this one. Pull that out, put a 1. All right, there we go. Okay, next. Well, look. The derivative of x plus 2i is 1. Okay, so by substitution, this integral right here is going to be the natural log of x plus 2i. Okay, so I'll write that in. Log. Was it x plus 2i? I need a space or a multiply sign. Get rid of the brackets, too many of those. Okay, and this one will be the log of x minus 2i. Okay, now that we've completed that, plus constant c. Okay, now you might want to remember log rules. Okay, but we can factorize out. We can factorize out this 1/4 of I. Okay, so let's do that. All right, now we've got a difference of 2 logs. So when you have a difference of 2 logs, you can express that as the log of a fraction. Okay, so I'll open up the palette, find a fraction symbol, press this button, okay, get rid of the palette, and then, oh, hold on, that was a minus, wasn't it? So let's fix that. Whoops. Okay, so copy, paste, paste. Alrighty, so we've simplified this a little bit. And now you might want to make the denominator real, okay? So there are further simplifications you can do, right? Because remember, we found something that looked a little bit different when we did this by trig substitution. Okay, so what did we find by trig substitution? We found 1/2 arctan of x on 2. All right, so this should be equal to this. All right, but you would have to do a lot of simplification to find that those two are equal. All right, maybe this is a little bit too much to go into at this stage. Right, so the question now is, can we ask Mathematica, are these two the same? All right, and what will it say? I don't know if it will say that they are. Perhaps I can ask it to simplify. Shift enter. No, okay, that didn't work. That doesn't work either. Okay, anyway, these should be the same. All right, so there are a number of ways to calculate the integral. Okay, that's all I have for you for now. I hope you learned something, and I'll see you next time. Bye for now. Oh, hey, if you were struggling to show that these two are the same, what you could do is just test out numerically, you know, conjecture that they may or may not be. Okay, so let's copy this quantity, come down to a new cell, copy that, copy the other one, the comma between them, and let's turn that into a pair. All right, so what happens if I say replace all? And let's replace x with the number 5. Okay, well, so we want numerically, so 5.0. All right, so you can see, no, not the same, okay? But they may differ by some number. So let's try 6. 6. Shift enter. Okay, so this is essentially a real number because this imaginary part is so tiny it doesn't matter. It's probably not really there. Okay, so now that suggests that maybe they are the same, but they differ by a constant. So let's subtract. Okay, so now what happens if we add this to the expression plus this number? Okay, so it looks to be just about 0 now. Now if we change the value of x, is it still the same? Let's go 7. Yep, still looking like 0. Let's go 7,000. Yep, still looking like 0. So it's roughly, we roughly find that this is equal to 0, right? For all real x. So that's just a conjecture, right? You'd still have to go and do the hard work to show that those two are the same. All right, now if we're to rearrange this equation, we find that this is equal to this, no, minus that. Okay, something like this. All right, so that's okay because these are just two different constants. So let's say this is C1 and this is C2. All right, so that's all correct. Probably, right? You still need to go through and verify this using algebraic identities. Okay, Bye again. See you next time.